So it's me again, Ling from Louisiana State. So I talk about Whipple's formula revisited. This is a drawing work with Winnie Lee and Fountain 2. And I'm actually only prepare very few slices so that I'm not going to make it very technical. The whole point is hopefully towards the end, you still know what I'm talking about right here. Okay, so let me start. So hypergeometric objects now has been developed from the classical hypergeometric functions, hypergeometric differential equations back to the time of Gauss, Kummer, etc. And in the 90s, there is development on the hypergeometric Galois representations and L functions start from the work of Nick Katz. So he constructed L at the shift correspond to what we call hypergeometric data. And later, David Roberts, Fernando Rodriguez Villegas, and Mark Watkins, they actually use hypergeometric data and the corresponding L function to construct families of very nice L functions, very highly computable. There is even magma implementation called hypergeometric motif, which are actually very useful when we're trying to test out different kind of new ideas on the subject. And there is another level called hypergeometric character sum identities. So there are many amazing identities relating more or less very much like what you have seen on Whipple's formula later. There's a left-hand side, there's a right-hand side, but they're written in a way it's kind of could be technical at the first glance. And so basically this kind of approach, and around the same time, Nick Katz is the John Green have written a paper called Hypergeometric Function over Finite Fields. He actually kind of have a way of writing down many classical objects in the setting of finite fields. And his function was later modified by Dermot McCarthy with some kind of a nice modification. And based on McCarthy's modification, Fritz Boyker's, Henri Cohen, and Anton Manet, they actually kind of build further the corresponding definition of hypergeometric functions when the motif or the data is given over Q. So this is a definition that they generalize from a priori Galois representation for absolute Galois group of cyclotomic field. For the cases when it's extendable to absolute Galois group, they made the definition more general. And in around 2014, I and my collaborators, Jenny Fuseli, Ravi Ramakrishna, Hollis Risher, and again Fountain 2, we gave more or less a dictionary for how to approach some of the classical formula using a very straightforward dictionary method. And my colleagues, Bill Hoffman and Fountain 2, they also use the rigidity to attain hypergeometric identities. There is another sign which is called the p-adic hypergeometric functions, initiated in the work of de Waal. And it's also pushed forward by some very influential conjectures, including some conjecture made by Fritz Boykers on the A-prime supercongruences occur to A-prime numbers, which was proved by Scott Algren and Ken Arnold in 2000. And later, there are further developments by Kilburn, McCarthy, myself, and Ravi Ramakrishna brought forth a so-called p-adic perturbation method, which is kind of useful for proving certain type of supercongruences that I'm going to tell you more about what that is. And so also I'm going to, in the motivation, I'm going to talk about this paper over here. And now let me get to the motivation. The part, my talk is mainly number theory. The only thing connected to mirror symmetry is more or less the motivation that we know around the time in the late 90s and 2000, the mirror symmetry has been kind of computed extensively on Fermat quintic family and its mirror. So the first one to us is so-called the Fermatine equation with a deformation, one parameter deformation. And this family below is the Fermat-Quintic. And the relation in between will be, you start out with this hypersurface, you move out, there is a natural automorphism group, including you can insert fifth row unity to x1. You can do that here, here, and here. But the last one, the choice, have to be compatible so that the mixed term somehow will be invariant if you're adding the fifth row unity. So the quotient more or less will give you the equation down here below. And the Fermat-Quintic and its mirror play a very important role. In the literature, there are extensive studies of both cases. So I'm going to focus on the Picard-Fuchs equation for either case over here, especially for the mirror. It's going to be, I forgot about that, equal to 0 over here. I'm sorry about that. And for the mirror, the Picard-Fuchs equation, that means if you computed the differential, so this is a Calabi-Yau threefold. If you compute the differential, holomorphic differential threefold and around any chosen cycle, you will get the solution depending on lambda, which is psi to the -5. One of the solution, the Picard-Fuchs equation has only 3 singularity if you use lambda, which is hypergeometric. One of the solution, which is unique, near 0 and holomorphic, up to scalar is this one down here. It's a 4f3 with 4 upper parameters, and then 3, 1 below with another additional one, which is hiding. You can write down term-wise in terms of factorial very explicitly, and then the argument lambda is lambda to the k. So you have this implicit summation. And it's only one of those so-called the Calabi-Yau equations that's specialized. If you have all the one below, and the upper one, there are 4. And then there is additional assumption called defined over Q. We're going to see that later. And altogether, there are 14 such Calabi-Yau equations. You can find such a list, for instance, in this paper by Elkvist and Van Kerkhove, Van Straten and Zudenek. And in particular, in 2 very important papers by Candelas, De La Osa, and Rodriguez-Villegas, they computed zeta functions for the Quintic family. For given a parameter psi, they computed the zeta function, local zeta function very explicitly. In the process of computation, of course, the zeta function will have numerator denominators coming from different cohomology groups. They identify an essential motif, which lives in the 3rd cohomology group with Hodge number. If you look at the sequence over here, it's going to be Hodge number H30 to be 1, H21 to be 1, etc. So this is one of the 4-dimensional motif, giving rise to degree 4 factor on the numerator. And for this talk, what I'm going to just use, this is one of the kind of easy factor compute will be, if I'm going to fix the parameter to be z for number series so that I can talk about the global kind of Galois representation. And once I fix parameters, then I can talk about the fiber. The fiber is going to be a Calabi-Yau threefold. If I let this m sub p to be the number of points of this variety, we can simply take the equation and count how many solutions there are over a finite field fp. That for any prime number that's not divide phi and the parameter, the number of solutions, if you do the naive count, it's going to be congruent to the same hypergeometric function. Here, lambda is written as psi to the -5. And the subscript p-1 means I'm going to do the truncation. Instead of doing the summation k from 0 to infinity, I stop from k from 0 to p-1. So it's going to be a finite sum. This finite sum is playing the role of Hasse invariant for number series. then both hand side, the count over here, will agree to the truncated hypergeometric value modulo P. So this is a generic kind of congruences. It works for any fiber. You pick any integer psi over here, then this generic congruence will hold. In particular, when you get to the fiber, when it satisfies the condition, psi to the 5 power is 1, then the corresponding fiber is a singular fiber, what they call it's a quintifold. So it has actually, for the quintic family, there are 125 ordinary double point. And the corresponding motif, generically, the motif is of the 4-dimensional with this Hodge sequence. When you get to the special choice, psi to be 1 or psi to the 5 power equals to 1, the motif degenerates into 3-dimensional piece and has a decomposition into 2 motifs. One has Hodge sequence 1, 0, 0, 1. The other is 0, 1, 0, 0. And when you pick the value psi to be an integer, for this case, there's only one choice, which is 1. And check also that this corresponding algebraic variety defined over Q is modular, in the sense that if you compute the Galois representation arriving from a 2-dimensional piece from the third atypical homology, it corresponds to the Galois representation arriving from a wave for level 25 Hecke eigenform. And the label at the L function and modular form database is F. 25 stands for the level, 4 is the weight, A means it's a trivial character, B is the second one. And if I interpret the generic congruence using this new idea of the modularity, what we will get is basically the same kind of right-hand side, I write it down, and the minus side go to the other side is negative. The piece coefficient, the A sub P, stands for the piece coefficient of this modular form, modulo P. So this is the generic congruence, which is not surprising. All the fiber will more or less behaving like this manner over here. But what Rodriguez-Villegas discovered was something kind of interesting. He discovered that actually when P is bigger than 5, the generic congruence is actually far too weak. Both hand side will actually agree modulo P to the 3 power. So if you do the truncation to P minus 1, comparing with the modularity, I don't know what happened, but it zoomed in. So let me see. Zoom in. Okay. Can you see properly? I'm sorry.
Yes.
I don't know what I touched, but he actually saw that for any P bigger than 5, the two objects, one is the truncated hypergeometric function at P minus 1, playing the role of Hassard invariant. The right-hand side is the piece coefficient of this waveform modular form. They agree modulo P to the 3 power. And it is called a supercongruence. It means that it's actually much stronger than what the generic congruence tells you. And he discovered this, and along with, I mentioned there are 14 Clapeyron equations. And he actually also made the conjecture for other 13 cases as well. So in 2017, my colleague Fanting Chu again, Noriko Yuri, and Wading Zudelin and I together proved that his conjectures were all true. And previous work on his conjecture has been done for 3 cases by Cuban, McCarthy, Fuseli, and McCarthy for 3 cases. And once we make the announcement that we solved his conjecture, David Roberts and Rodriguez-Villegas, we were at the Matrix Institute at Australia at that time. So they work very hard and make a new supercongruence conjecture. Their conjecture is actually giving a heuristic of how do you predict the 3 up here. They predict that the 3 happens because of the hypergeometric motif where this truncated hypergeometric function lives in has a Hodge number gap. For instance, in the background for this corresponding supercongruence, the corresponding motif actually has Hodge number 1001. The Hodge number gap means from this one and that one, the distance is 3. So this actually tells you the strength of the supercongruence. But in general, it's very difficult to prove. And it's also very difficult to find how do I change the one so that I get something similar. The question is not easy. So it's actually becoming the motivation of my talk. I was trying to find kind of hypergeometric motif which are decomposable with a large Harsh number gap. All right. So that's the particular motivation for this talk. And one way of doing that is to use Whipple's 7F6 formula. Okay. Is there any question before I continue?
Maybe ask, does this 786 appear in a related Calabi-Yau, or that is going to be the point of your talk?
The Calabi-Yau, there are actually, if you move on, if you rearrange the parameters, you could get to something which is a Calabi-Yau, but it's a 5-fold. You can get something.
Yes.
Yeah.
Okay. Thank you.
All right. So let me actually get back to the basic notations. And basically, the gamma function, we defined it as an integral. The way I want to mention it is because in the integral over here, if you fix x, if you're taking the integral as the variable t, there are 2 parts. This part, e to the minus t, is an additive character of t. The other one is a multiplicative character. So it's a coupling of 2 kind of additive and multiplicative characters. So when I get to finite field, which is the main object for today, so which the settings switch to FQ will be a finite field of characteristic P, I assume to be bigger than 2 for convenience. So we are going to use the hat F clause over here, which means invertible elements. The hat means all the characters, so it's homomorphisms from invertible element to any C or CP, which is algebraically closed field doing the invertible elements. So anyway, this is a cyclic group. So we can fix a generator for this group of multiplicative characters. And once you fix a generator, then each element is of the form the generator raised to a power. The power ranging from 0, 1 all the way to Q minus 2. And the Gauss sum is well known to be the finite field analog of gamma function. So it's defined in a very similar manner. So what you do is, for given kind, which is a multiplicative character, we first fix a additive character, which is first you take the chase function from finite field FQ down to its prime field. So you get, using the chase method, you get one element in FP, and then you apply it to any fixed primitive piece root, you get the additive character. Then the Gauss sum is defined to be the couple between the fixed additive character and your choice of multiplicative character. And somehow you can see from the definition, they look very similar. And they also satisfy very parallel kind of conditions. For example, the reflection formula, both gamma function and Gauss sum satisfies that, and also the multiplication formulas. And why Gauss sums for number theories or point counting? Right, here's a good kind of quick answer for this. Why Gauss sums for number theories? They are fundamental for finite Fourier analysis. For instance, if I get back to the point count at the beginning, which is counting how many solutions the quintet family for a fixed fiber, how many solutions there are. One way to do it is we add additional variable U. So if I kind of doing the summation, applying the additive character to this product, in case if I plug the value x1 to x5 in here, I get a value which is not 0. Summing over U, the average will be 0. So on the other hand, If the xi, when I choose, give me the right solution, the u, doesn't matter which u I pick, the value is always 1. So it's actually giving me a delta function of computing number of solutions. And the p means, because due to the u, p minus 1 is due to its it's actually conversion from the homogeneous model to the R5 model over here. And now once I write in this way, there is by default, there is additive character. And for any multiplicative character, if I do the finite Fourier analysis, I do the inner product. So if I do the inner product, then I can easily convert the right-hand side easily into a kind of combination of Gauss sums. And they're playing the role of more or less what we've seen before is binomial coefficients before. All right, so let me formally kind of introduce the players for my talk. I'm going to forget more or less from now on the models, the algebraic models. You might have the quinty or the mirror. And the point of hypergeometric motif is it doesn't quite matter. We can compute the L function. We don't need to remember which model we start with. So a hypergeometric datum consists of three players. First, alpha is a multi-set. So the multi-set consists of lists of elements, which are, for this talk, rational numbers. Beta is another multi-set of the same length. And for our convention, the first one is fixed to be 1. And other are all chosen to be rational numbers. And they could be the same. The ordering doesn't matter right now. And the other one will be lambda for my talk, because in the background, I still have varieties. I still want them to have algebraic variety defined over some, it's algebraic number. So in general, it could be in C. Once I fixed this set of rational numbers, AI and BI, I will let M to be the least positive common denominators of all AI and BJs. So this is actually telling me when I later compute Galois representation, what will be the corresponding field. The field will be the underlying field will be Q joining the primitive M's root. M again is the least positive denominators. And now here's a few more terminology which are useful for our application. One is such a multi-set alpha is said to be self-due if we look at the corresponding polynomial attained by a formal variable x minus the corresponding vector unity computed from AG. So I have n of them, I take a product. If the coefficients turn out to be real, then I call alpha to be self-due. And such a multi-set is said to be defined over Q if this polynomial further have z coefficients. For instance, if I take this alpha to be a multi-set of 2 elements, 1/5 and 4/5, if I write it down, then the coefficient will be totally real. So it's going to be self-due. And on the other hand, if I look at the second example, if I pick 1/2, 1/3, and 2/3, this combination giving me a multi-set which is defined over Q. And now if I put together a pair, the pair alpha beta is said to be self-due if both of them are. And the pair is called primitive if the difference between any AI and BJ, including 1, the difference is not an integer. So this is the notion for self-due and primitive. And the hypergeometric datum, when I look at the 3 players altogether, is said to be defined over Q if both multi-sets are defined over Q. And lambda is also an element in Q as well. So under that setting, we're going to get Galois representation for the absolute Galois group GQ. Okay, so these are the basic setups. Any question before I move on? All right. And now, once you have alpha beta, which is given two multisets, the classical hypergeometric function, as what we mentioned, is defined to be this formal power series. And you're going to put the upper parameter on the top, forming by rising factorial. They are actually quotient of gamma functions. As what I tried to illustrate, gamma function will play a fundamental role. So the rising factorial or the Pochhammer symbol A sub k is gamma A plus k over gamma A. So it's A times A plus 1 and all the way to A plus k minus 1, so k of them. So it's a generalization of the factorial function. In particular, you put 1 here, you get the k factorial. And if you look at this, if you fix alpha, beta with the same length now, if you let lambda considered as a variable, then it's actually very easy to verify it satisfies an ODE, which is ordered to be the length of the alpha set, with only 3 singularities at 0, 1, and infinity. And the local monogeomics are very clear. And in particular, for such a differential equation, if you look at solutions avoiding the singularity at any good point, the local solution will be n-dimensional. So this is the basis that you can build monogeomic representation. And what we have seen before is the truncated hypergeometric series. If I put a subscript, that means the truncation. I'm not going to infinity, but go to where the subscript telling me. So this is truncated hypergeometric function. Now let me get to the finite field side. So over a finite field, now if I put additional assumption, the size of a finite field is going to be congruent to 1 modulo m, again, is the least common denominator of alpha and beta. Then each of those product ai times q minus 1 or bj times q minus 1 will be becoming integers. So we clean off the denominators becoming integers. So now if I fix a choice for the generator of the multiplicative character, we can write down very analogous to the definition of classical hypergeometric function, a formal kind of character sum in terms of Gauss sums. So G applying to those characters arising from AI, and with additional k's playing the role over here, k, like the one above. So you can actually do a formal definition of character sum. So on surface, it just, you make a formula which is very parallel, but turn out to be deeper than they appear to be similar. And of course, in this definition over here, there is a condition where the condition is when Q is going to be 1 modulo, the least common denominator. However, when we look at the case, alpha, beta are both defined over Q. Say if lambda is coming from a global kind of rational number or integer, then this definition, we can lift the whole definition using multiplication formula of Gauss sum to be independent of this definition. So this formula can have a lift to get rid of the assumption under the special assumption when both alpha, beta are defined over Q. So this page telling us that there are kind of different players you can do, which was very analogous to the classical hypergeometric function, in particular, the finite field analog. You can compute very explicitly. Okay, any questions before I move on? All right. And now another thing, basically I want to say is, of course, I'm telling you, you can write down more or less by dictionary how to go to the character sum. On the finite field level, it could be pretty ad hoc at the first glance, but you can make it very systematic in the way that what I'm going to do is, again, it's the same setup. If I have alpha, beta as before, m is the least common denominator of ai and bj, I will let zeta of m to be a primitive n-square unity. Now I'm going to get to the level of Galois representation. So basically, again, the field, the cyclotomic field will be Q joining zeta m. So if lambda is a cyclotomic integer in this field, which is not zero, one systematic way to get finite field analog will be as follows. What we're going to do is for any non-zero prime ideal, which does not divide M, we're going to look at the residual field. So this is the one way we could up residue, the finite fields from residual field. So for any fixed prime ideal, you pass on to the quotient. It's a ring of integers of the cyclotomic field. You go to the quotient field, and by construction, the quotient field automatically will satisfy the assumption it's going to be 1 modulo the degree of the cyclotomic field. And if I fix a generator of this residual field so that when I apply this generator to the primitive answer of unity modulo p, the value is going to be zeta m to the -1 power. If I fix such a choice, then there is a systematic way I can pass out the AI to characters to the residual field, Bj also to the characters on the residual field. And if I define this way, the definition is independent of how I'm going to pick the omega. The value will be always the same. So this is a systematic way, depending only on which prime I do, I'm going to use, as long as everybody agree to the common rule over here. We will get a way assign finite field analog to any finite field coming as a quotient. And let me kind of mention some of the more classical examples, how this different aspects are timed together. So if you get to, this is called the Legendre family of elliptic curves. So the way you see is K is a parameter. If you fix a K, which is different from 0 and plus minus 1, and if X is the parameter in CP1, Y square is going to create a double cover of CP1, avoiding X to be plus minus 1 and X to be plus minus 1 over K. So it's a double cover ramified at 4 points. So what we'll get will be an elliptic curve. For fixed K, you can write down two differentials corresponding to the elliptic curve. One is omega 1 is dx over y. The other one, omega 2, is 1 minus k squared x squared dx over y. The first one is holomorphic, the second one is not. They span the first rank cohomology of this elliptic curve. So if you're going to take a cycle, because here, so if I take the cycle 0 to 1 over here and doing the integration, what we'll get, in addition to the transcendental part, we will get the 2f1, 1 half, 1 half, and 1 here, with the argument to be k squared. And the second one, the second period we're going to get will be a very similar one with the same kind of transcendental degree, and the parameter here is -1 half. And the second one turns out can be attained from the first one by taking derivative. So the second period can be attained more or less as a derivative of the first one plus a combination of the first one. They are relating by so-called the Legendre relation. And on the Galois side, when k is an rational number which is different from 0 and plus minus 1, what we have will be an elliptic curve divided over q. Then for any fixed prime number L, you can compute the so-called Galois representation. The Galois representation will be two-dimensional, arriving from the L division points of the elliptic curve. And if you compute for the Galois representation, if you look at the semi-simplification, the most important thing will be computing traces. For Galois representation at unramified prime, you compute what we call Frobenius. The trace of Frobenius under for this particular Galois representation arriving from elliptic curve, it turns out to be nothing but the character sum corresponding to the multi-set alpha, which is 1/2, 1/2, and beta to be 1, 1, and k squared, which is consistent with the complex periods. The complex periods corresponding to the same kind of multi-set with alpha to be 1/2, 1/2 on the top, beta to be 1, 1 down here. So what I'm trying to tell you is the classical hypergeometric function and the character sum, they're appearing in a compatible package. That's what I'm trying to convey here. Any questions before I move on? Okay. All right, so, and kind of one very fundamental and crucial kind of result to the everything I'm going to talk about later will be this combinations of a lot of results. It's a theorem I attributed to Katz, Nicholas Katz, Fritz Beukers, Harry Cohen, and Anton Manet. So the setting is if you have alpha beta to be primitive with the same length, again, if I let m to be the least common denominator of alpha and beta, if I fix lambda, which is integer, which is not 0, L is a fixed prime number. And another assumption we're going to put is how many elements in beta, they are kind of like 1 integers. So once you have everything on the table, then you can compute. So the conclusion will be then there is a finite dimensional Galois representation. Gn will be the absolute Galois group of Q joining the primitive nth root, the absolute Galois group of the cyclotomic field. Okay, so this is the notation for that particular absolutely Galois group for the cyclotomic field. And the conclusion is for any unramified prime, so when P is not dividing the least common denominator, such that it's also the order of P dividing lambda, it's also 0, then the finite dimensional Galois representation is characterized by the property a Frobenius element is trace, is more or less determined by the finite field analog of the hypergeometric sum, plus possibly some power of Q. And in one of the examples we have seen before, when alpha is 1/2, 1/2, beta is 1, 1. So these two numbers are the same. So this part will be 1. And plus, sometimes there might be additional finite order character. Right? So basically, this A item means the importance of hypergeometric functions over finite field. Basically, it's because they are traces of Galois representations, which are finite dimensional. And in particular, yeah?
Sorry, are these Galois representations supposed to be automorphic or?
Actually, if these Galois representations are all kind of motivic. Oh, so Lemmon's program actually tells you they should be automorphic. We are going to tell you the cases we know for sure which are automorphic.
Okay.
Automorphic later. All right.
Okay.
So this is actually what I'm trying to demonstrate. It's a good source of very combinatorial way and very explicit way you can compute L functions by using very not much input. What you need will be some alpha, beta, and lambda. That's it. Then you can run the program. In particular, the dimension. Let me get to the dimension. When lambda is not 0 and 1, the dimension will be the same as the length of the multi-set alpha and beta. And it's also the pure case. All roots of the characteristic polynomial of the Frobenius will have absolute value q to the n minus 1 over 2. However, when lambda equals to 1, due to so-called there is a Cauchy reflection, dimension will be dropped down to 1 less compared to the generic case as what we have seen for the quintic case. Originally, it's 4 and then dropped down to 3 when lambda equals 1. And moreover, this 1 less dimensional Galois representation also might have a primitive part. The primitive part might be a little bit smaller. So the dimension is 2 times the floor function of n minus 1 over 2. Okay, for example, what I'm going to see will be 6. In this case, D is going to be 4. And when I pick lambda to be 1, for alpha set to be length 6, the corresponding representation is going to be 5-dimensional. And in particular, it has a primitive part, which is 4-dimensional plus a 1-dimensional representation. So it's already decomposable. And Fritz-Boyke's, Cohen, and Menis kind of contributions mainly comes in the last item. When the alpha beta are defined over Q, then this character sum can be lifted to all the Frobenius over FP. So it has the Galois representation can be lifted to GQ. And the formula can be written using what their formula telling you, using the multiplication formula. You can write down a formulation which is independent of the requirement Q to be 1 modulo M. So this is in addition, if you look alpha beta divided over Q, then the representation a priori is for the cyclotonic field can be lifted to the whole Galois group. Right? And the dimension will be the same as what we mentioned earlier. Okay? So which is the key point over here? It's actually one of the very fundamental results telling you, here, if you're telling me the correct player, then I can build different things which of interest to myself, right? Any questions? Any more questions before I move on? Okay, all right, finally, I got to Whipple's formula. All right, Whipple's formula. Now let's look at Whipple's formula one more time. So this is Whipple's formula says that if you start with something which is 7F6, all right, and the parameters are written this way over here, and if you check quickly, by default, if I look at alpha and beta, alpha beta consists of adding 1 over here, both 7 elements, but it's not going to be primitive. Primitive means any AI minus Bj shouldn't be integer. But this two, if you take a difference, it's 1. So it's not primitive. On the character sum level, they correspond to the same character. So what we're going to see from the finite field analog, you can cross off these two, which correspond to the same character on the finite field level. All right. And so this is 1. After I cross off this 2, I get to 6 parameters on the top, 6 down here at value 1. So as what I mentioned earlier, in the background, there is a 5-dimensional Galois representation, which is decomposable. So it's going to be 4 plus 1, which is on the left-hand side. And the right-hand side, if I'm going to use kind of more or less the spirit of the previous slides, it's going to be something 4-dimensional, but it's at 1. So it's a 1-dimension job. So it's going to be on the right-hand side. It's an object of 3-dimensional. And because of 1, again, it decomposes into 2 plus 1. So this formula already telling us that there is an object on the right-hand side, a priori is 4 plus 1, somehow agree with something on the right-hand side, which is 2 plus 1. It doesn't seem right, right? So we're going to explain what's happening, right? So I have mentioned that the 7F61 is imprimitive because of the difference, it's 1. And the 7F61 is well posed in the sense that if you're adding the parameters in the same column, A plus 1 is A plus 1. A plus 1 half over 2 plus A over 2 is 1 plus A. And here again, you add that up. Each column added up is 1 plus A. So it's called well posed. There is a very special property about well posed series. Another way to say it's basically, if you write down your A, your beta can be obtained in the way it's 1 plus A minus AI. This is another way to write down beta. So this formula is widely known, is widely used. I use it quite a few times myself. It's really useful for superconferences. Okay. So I'm going to see what happened. I want to construct something decomposable. This formula tells me, yes, potentially there is something going on for the motif on the right-hand side, which is decomposable. Already it's 4 plus 1. And the left-hand side telling me it could be decomposed further. Right. And now I'm going to add the self-due assumption. If I want to get Galois representation, eventually my Galois representation will be defined with Q, so they're all self-due. Right. Self-due will give me some very nice symmetry, additional kind of additional symmetry. So to get to self-due, more or less what I want will be the parameters will appearing by pair. If I see A, I will see 1 minus A. If I see B, I will see 1 minus B, etc. to get something self-due. For that reason, I assume that C plus D add up to 1, F and G add up to 1. This is one way. If I get all the 1/2, it's fine. 1/2 plus 1/2 is also 1. So to get to something self-due, naturally we assume they pair up. If I see C, I see 1 minus C, etc. And I would like the self-due property on the lower parameter as well. And that's pretty restrictive. That means beta is more or less 1 plus A minus AI. I do not have too many choices for what choices A I need to pick. More or less, it forces me to pick A to be 1/2 and also E to be 1/2 as well. So the specialization relating to the formula, I still have, after specialize A to be 1/2, my formula will look like 1/2. I have this thing which is going to cancel out each other. I have C, 1 minus C. I have this little p over here. It's just a technical thing to make it to be a negative number because my p is an odd prime number. So it's a negative number to make sure both hand side terminates. All right. Theoretically, I consider that as 1/2. So I get to, on the left-hand side, a hypergeometric motif. The length of my multi-set will be 6 of them. It's 1/2 after I canceling out the 5/4 and 1/4 corresponding to the same character. I get to a hypergeometric motif, which is 1/2 C, 1 minus C, 1/2 F minus 1 minus F. And down here, I have another hypergeometric parameter, which is also defined with a Q, put into the formula, is defined with a Q. And the argument, which is, this is Whipple's formula, is 1. And now I get to the right-hand side. The right-hand side, so far I only use self-due. It brings down to something which is also self-due. So on the right-hand side, it's 1/2, 1/2, F, 1 minus F, which is good. And then the beta says 1, 1, more or less 1/2 minus C and 1/2 plus C, which is also defined over Q with argument 1. Okay, so we have now 2 Galois representations. This, as I mentioned, is 4 plus 1, and the right-hand side is 2 plus 1. Okay, any questions so far? All right. So basically, another player we don't see is there is actually another thing, which is 3F2, corresponding to another hypergeometric motif. Again, it's defined over Q. The parameter sets 1/2 F, 1 minus F, 1, 3/2 minus C, and 1/2 plus C. And then there is also a player called the Clausen formula. The importance of Clausen formula basically is the 3F2 can be written as product 2F1, which more or less, they are actually, in terms of Galois representation, they are more or less up to a character isomorphic. Right. So basically, I will need this formula so that I see the parameters gets a little bit more complicated when I get to the May theorem. All right. So there is additional intermediate player you don't see on the surface of the formulation. But here is our theorem, Whipple's formula in terms of Galois representation. All right. So it says that so far everything, I'm going to do that on the level of self-due. If we have any choice of C and F, which are 2 rational numbers, such that the corresponding hypergeometric motif on the left-hand side and right-hand side both primitive, right? Now I'm going to repeat the same thing for this capital letter N, which is the least denominators of the first one, the second one, it doesn't matter, two hypergeometric motifs. There will be another integer correspond to the third hypergeometric motif, the least common denominator. It could be either the same or could be double for most of the cases. And now for the first hypergeometric data with argument 1, we get to a 5-dimensional Galois representation. And Cass' theorem tells us that it's going to be 4 plus 1. And the right-hand side is 2 plus 1. And what's really happened is as follows. If you look at the Galois representation, which is 5-dimensional arriving from the hypergeometric data on the left-hand side is 5-dimensional. If you do a further restriction, possibly you need to restrict to an index 2 subgroup coming from an intermediate player, then what you will see is it decomposes further into 2 pieces. They're indeed a 3-dimensional piece, which agree after restriction, the right-hand side up to a Tate twist. Plus, there will be another 2-dimensional Galois representation. So basically, the Whipple's formula in terms of Galois representation actually unraveled to be a relation among Galois representations, something 5-dimensional as what we mentioned to start with. After you do a suitable restriction to possibly index 2 subgroup, it turns out decomposes into 2 pieces. The first piece is 3-dimensional. Up to a Tate twist is the right-hand side. And additionally, there might be a 2-dimensional Galois representation, right? So let me put together the comparison between the classical case and the formulation we obtain. So basically, in the classical formulation, after I specify the parameter to make things to be self-due, we have 7f6 at 1, agree with this 4f3 at 1 up to a p factor and gamma factor. And what we see over here is the corresponding Galois representation, which is 5-dimensional. After restriction, agree with the right-hand side with a Tate twist. And the missing part you don't see will be there is additional 2-dimensional Galois representation, which turns out to be the major term. All right. So everything can be computed explicitly. All right. So let me tell you, actually, I don't want to go through the proof. It could be a little bit technical, but the key idea is hidden in this very innocent looking formula. All right, if you have this 6p5, which is another way you write down the character sum, it's a p function, which is more convenient way to do the character sum computation, where all the A, B, C, D, E are characters. If it's a well-posed again means the product to be the same thing. All right, the well-posed over here is what you see is A times it. So I actually the well-posed, you have to shift it a little bit. Under the well-posed assumption, we shifted the terms a little bit. And after we're dropping the terms, which are actually different by 1, we get to 6f5. You can read it as 6f5 up to a normalization. Basically, this 1 can be computed by this formula. The most important thing about the right-hand side will be it's going to be fiber-wise. It's going to be 3p2. 3p2, which means I'm talking about finite hypergeometric functions with 3 upper parameter and 3 lower parameter with a square. What we are actually seeing is something 3-dimensional generically. The square means it's going to be a tensor product. So fiber-wise, you can decompose into symmetric power and alternating squares. If you decompose the right-hand side, consider that as the trace of a symmetric square into the trace of symmetric square and alternating square, you have a natural decomposition, which is Galois, okay, which is compatible with the action of Galois. So which actually give you the formula I mentioned in the previous page. So the decomposition the symmetric square part give this two-term, the two-dimensional Galois representation. The other part, the alternating part, give rise to the three-dimensional Galois representation. So then it's actually how to kind of match up the terms carefully to see how everything will work, right? So which is the key idea, why things will work. It's due to, it's a special way to compute the character sum. It's this way, fiber-wise, it's a tensor product. Our choices will guarantee the HD3, the third hypergeometric data is also self-due. So everything will work well. It's going to be a tensor product. So it has a natural decomposition. Right. Any question? Okay. So no, let me go quickly. Then we go further because eventually what we want is what you have mentioned. How about whether there is automorphic and etc. So that's also one of our main interests anyway. And so we specialize further. So the previous theorem is for any CNF. And now we would like the hypergeometric data to be defined over Q. To make things defined over Q, then I have to be a little bit more careful. I want the whole thing add up together to be relating to the choices. The Euler phi number of the denominator cannot be bigger than 2 or 4, either 2 or 4 or 1, right? So anyway, under the assumption, I want something which is defined over Q and primitive. It boils down to only 7 choices. All right. For all the 7 choices, we compute explicitly the corresponding left-hand side, which is so the left-hand side, when we compute, it's a 5-dimensional Galois representation. Right? And indeed, it decomposes into nicely. It's a 2 plus 1 and plus another 2. So everything's automorphic. Under the assumption, then we identify the corresponding modular forms very explicitly. For instance, when the upper parameters 1/2, 1/2, that's what you call it, you correspond to a Calabi-Yau threefold, you can write down the equation. Right? We can write down the equation. And so the generic part, which is coming from the symmetric square, is actually a level A V6 modular form with trivial character. And the part from 4F3, because of the additional P, is going to be a level A V4 modular form with trivial character. This is the one-dimensional representation, so everything decomposed nicely, but there are different phenomena. You see, I highlighted this one comparing to the next one. The next one over here, it's going to be look differently. You have a P times, now the Galois representation correspond to a modular form. It's only wave 4, level A, with additional P here, right? So this is according to the decomposition, we're able to prove very explicitly each cases will be automorphic. So this is the corresponding modular forms, right? So let me get back to the motivation, all right? My motivation is why I was trying to find Galois representation which are highly decomposable. Right? So actually in the literature, the first character sum correspond to 1/2, 1/2 on the left-hand side can be written in terms of 2 piece coefficients and P power was first conjectured by Koike and was shown by Sharon Frechette-Keono and Matt Papanikolaou. And if you can see clearly from the decomposition, the corresponding hypergeometric motif is 5-dimensional, has a decomposition. The Hodge sequence, the corresponding Hodge sequence will be 1, 0, 0, 0, 1 for the first one because it's wave 6. And the second one is wave 4, so with a P, so it's a 0, 1, 0, 0, 1, 0. And the last one, it's a 0, 0, 1, 0, etc. And now according to the philosophy of David Roberts, Philando, Rodriguez, Villegas, you expect they agree the truncated hypergeometric function and the coefficient, the leading term agree modulo p to the 5 because of the Hodge number gap. In particular, when the conclusion was actually shown to be true modulo p to the 3 by Robert Osborne, Ming Straub, and Wading Zuderling. And numerically, we also identify the p's for the middle guy over here. So for the middle p's, if we look at going back to Whipple's formula, they do have the 5/4 and 1/4. If you add them back, they correspond to the middle p's. They agree with the middle p's modulo p to the 3. A priori is p to the 3, but with additional p here, so it goes up to p to the 4. All right, so it's more or less still compatible with their heuristic. All right. And we also actually computed exactly the Archimedean version in terms of real periods of those modular forms. All right. So the untruncated version turns out we call it to be the Archimedean version. It's the real periods of this modular form. All right, the real periods of this modular form, if you take it to be a very explicit cycle, it will be exactly the untruncated version. And then the second formula, we also identify the modular form. So this is the outside modular form. There are two modular forms, right? They will actually, the corresponding cycle will give you the untruncated version for the original Whipple formula and the Whipple formula with the 5/4 and 1/4 deleted. Right. And for the other case I want to mention, it's if you get to what I highlighted, the second case, it's 1/2 and 1/6. And the 5-dimensional Galois representation has a decomposition. The first piece, the major term with a p here, and it turns out to be more or less the same weight as the second term. So both of them correspond to waveform modular form, one of level 8 and one of level 24. And the corresponding hypergeometric motif decompose into 3 pieces accordingly, and they will behave the same. And in terms of supercongruence, we tested numerically. Indeed, this is very consistent with what they are telling us. There's the Hodge number gap from this one, the first one, to the next one. It's the distance 3, so it's p to the 3. So same thing happened to the second case as well. Right. So that's what we actually able to do. It's the motivation was trying to find something coming from hypergeometric motif, give me something decomposable, giving rise to examples of supercongruences. And in the end, we concluded Whipple's formula is one way we can do it. And the background is pretty geometric and give us very nice kind of Galois decompositions, which is compatible with the heuristic of David Roberts and Fernando Rodriguez Villegas. I think that's the end of my talk, and thank you very much for your attention.
Thank you very much. Are there any questions? Are there any questions?
I've got one. So if I understand correctly, the APs that you mentioned, maybe a few slides in the end, maybe 1 before. So in the when you go for when you go from when you go to an FP, so you go to a field of characteristic P, it stops. The point count are no longer modular Fourier expansion coefficients of some weight 4 modular form, but they are the p Fourier coefficients of some weight 6 modular form of level 8 and the p Fourier coefficient of a weight 4 modular form of level 8.
Yeah.
Okay, I see. So
we can predict the weight more or less, but the level we can only tell you like what prime factor should be there. It's relating to the 1/2, so we expect only 2 power will appear at the level.
Right.
We know the weight will be 6 but it could be some more twist going on. So we go back to this table over here. And some cases, the first 3 cases, the leading modular form has weight 6. And then there are 2 cases, the leading coefficient, the leading modular form has weight 4 with a Tate twist. And there are even cases, the leading one is weight 2 with 2 Tate twists. So there is what we call, this can be kind of computed using the Newton polygon.
Right.
Behavior can be computed by using the Newton polygon.
Okay. Yeah. Can I just ask how one would do that using the Newton polygon?
So basically you have, so we write down, so there is an explicit formula because it goes back all the way. Let me see if I can do it quickly down here. If I click the right one, the magic rule. Sorry. Yeah, here. Sorry. So it lies in this formula down here. When we pick everything instead of the character text value in C, but in CP, we can use the Gauss-Koblitz formula to write down the Gauss sum. Each Gauss sum, we can write down, use Gauss-Koblitz formula, you know, the p-adic evaluation. So there is a pi term. So it's a pi term and then it's gamma function. So you're putting together the contributions from all the pi terms. Pi is going to be a solution of x to the p minus 1 plus 1, going to be 0 in CP. But anyway, so this formula plus Gauss-Koblitz formula will tell you the behavior of the Newton polygon.
I see.
The explicit formula plus Gauss-Koblitz formula will tell you Newton polygon will look like what. It can be actually, they have a way to describe it. It's called the zigzag diagram. So it's pretty nice way of doing that. Let me go back to my main result. Okay. The application. Yeah. Say for instance, for the 1/2. So in this case, all the upper parameter will be 1, all the lower parameter will be 1. The zigzag diagram is you put together all the alpha and beta, as long as you only take their values within 0 and 1, you rearrange them in an increasing order. So I put all the 1/2 first and all the 1/2 later. Now we're going to go from 0. If according to the order, if the next one I'm going to use 1/2 is from the upper parameter, I go up, go up, go up, all the way till I get to 1, I go down, go down, go down. And then you will get to a kind of a triangle shape. Then you use the nodes where you're going up. You see the node you're going up and start from 0. The next one has high 1. There's only 1 node. So the Hodge sequence can be read off by using alpha and beta very explicitly. It's called the zigzag diagram.
I see. Thank you.
Okay, any other questions?
I have in principle one more, but I'm going to wait to see if anyone else has one.
Okay, go ahead.
Okay, so for me, one of the applications of Newton polytope is to construct the Calabi-Yau threefolds using the Bataillev construction. And you mentioned something about there existing a motivic story over here. I was wondering if you could say something about Calabi-Yau motifs using using Bataillev type construction and the Newton polytope, but based on the hypergeometric function that you mentioned here today.
So basically, I mean, go back to the motivation, right? And there are 2 kind of ways we can write down the equations. And once, I mean, there are different stories. Of course, one is attaining this equation, and then you do the desingularization, you do the point count, etc. So for us, the quick way, or for number theories, we are typically more familiar with this sign, which is Fermat or the walk family, etc. And actually, for hypergeometric motif, this sign is much more straightforward. The point counts on the second family is the toric, according to Fritz Boyker's, Henry Cohen, and Anton Mennet. And actually, based on cats, it's actually much easily you can compute the point counts on this sign over here. And what we did is actually we checked that using character sum, the computation more or less, the essential term will be the same. And so I don't know. I mean, what I can tell you is if you tell me the alpha beta set, I can tell you equations behaving like that. So that the character sum, the major part will be attaining from the formula. The formula will be the computing the major term. The representation will be as what it should be, and it will be the Galois representation. If I desingularize everything carefully, it will be on this model. Yeah.
I see. Thank you.
Okay. Well, if there are no more questions, let's thank the speaker again.
Thank you again for your attention. Okay.
Also, we have a break till 10:30.
Yep. We're going to stop recording now. Sorry.